Okay, so we talked a little bit about this yesterday. I want to take just a second and looking through this last night, I think it'd be worth maybe just reviewing how we can do this algebraically. So if we want to start here and end up there. We want to take this function and put it into this form, what we called standard form, where we can see what a and h and k are, right? Well, how do we do that? Just complete the square. So we'll start with our original problem. Let's call this a y instead of f of x, a little easier to write. So we get y equals x squared minus 10x plus 36. And our goal is to get it into this form, a times the quantity x minus h squared plus k. Well, the quantity x minus h squared looks like a perfect square, doesn't it? Right? So we've got to create a perfect square, and let's just take a second and review how we did that. We did a lot of this stuff earlier in the year. Remember that when we want to build a perfect square, we just have to start with something in the form x squared plus bx, right? And then we're going to add to those two terms just the right number to create a perfect square trinomial, right? So my recommendation is, before we do that stuff, let's just push everything else over. Let's get rid of all the other junk. Put it on the other side. So we'll subtract 36 from both sides to get rid of that. We'll store the 36 over on the other side, and we'll complete the square on the right side, okay? So we get y minus 36 equals x squared minus 10x, and then I'm going to add to that some number so that this is going to end up being a perfect square, right? So see if you can remember how we did that, right? If b is equal to negative 10, what's the number that's going to go with x in the perfect square? It's going to be negative 5, right? Half of b. So if b is negative 10, half of that would be negative 5. And so we're going to end up on the right side with x minus 5 squared. So h is going to be 5, right? But to get that, we have to add just the right number up here to the first two terms. So what's the recipe for that? 25. Because whatever half of b is, we're going to square it. That's b over 2 squared. So negative 5 squared is 25, right? Now we got to add it to both sides because it's an equation. So we have to treat both sides equally, right? So then on the right side, all of this stuff became x minus 5 squared. On the left side, we were just stuck with y minus 36 plus 25 is just minus 11. So what's the last step? Add the 11 back to the other side, right? And then we've got it. Then we've got y equals the quantity x minus 5 squared plus 11, right? So what's a? 1. It's the number out there, right? It's 1. What's h? 5. What's k? 11. We got it, right? Okay? So that's how we can do it algebraically. Now, there's a way that we could do this if we have access to Desmos, which I think you will on this question. There's another way we could do this too. We could even do a hard one like this where a is not equal to 1. So if we put in this function, let's call it f of x, and it's just going to be 2x squared minus 12x plus 26. Okay, so Ariel, if I'm in Desmos here, I can click on the vertex and get the coordinates. What's that tell me about h and k? 3 and 8, right? So we can see what h and k are just by graphing. I didn't have to go through the algebra of making that change. If I just graph the parabola in its original form, I can see that if the coordinates of the vertex are 3, 8, those are the values of h and k, right? And then if I want to find the value of a, let's think about that one. Now normally, if I were to graph the function, in fact I'm going to do it right here. If I graph the function y equals x squared, that's the parent function. If I scoot 1 to the right, how far up do I go? I go up 1, right? So I go over 1 and up 1. That's normal. A controls how much I'm stretching the function vertically, right? So now let's go up and look at our new function. We're starting at the point 3.8. If I scoot 1 to the right, how much is this going up? It's going up 2, isn't it? Right? And I could find that in a couple ways. So that's going to be the value. The vertex is at 3.8, right? So I want to know what the value of the function is when x is 4. So I could just come down here and do f of 4, and it gives me back 10 as an answer, right? So if that point is at 410, then that means it's right there, doesn't it? I've gone over 1 and up 2. So what's a? 2. Because I've stretched it now by a factor of 2. Instead of going up 1, I've stretched it so it's twice as far above the, right, above the vertex. Okay? Another way I could do that would be I could just graph the line x equals 4 and then find that intersection, right? So there it is at 410. And so now I can see both of those points. So I can see I go over 1 and up 2, right? So I found all three things there. I found h and k and a. But the good news is I don't even really need to find a because I already knew it. And I'll show you how. We could. Come on. There we go. Okay, so look at the original function. The original function is in the form f of x equals what we call general form, ax squared minus 12x plus, oh, sorry, I carried away there. Ax squared plus bx plus c, right? You see that? So what's the value of a? B is negative 12, c is 26. What's a? It's 2. It's going to stay 2, regardless of if I write it in this form or this form. Those are the same a's, right? So all I really needed to do was find h and k. I already knew that a was 2, right? Okay, so we got it. So the answer would just be, I'm going to plug in 2 for a, 3 for h, and 8 for k, based on the graph. Okay? All right. So we did this stuff. Now that's easy, right? All we're doing here, I'm just going to skip through a lot of these. This is one where all we're going to do here is we're just going to simplify the expression by combining all the like terms. So I'm just going to distribute the negative and then add up all the x squareds and the xy's and the constants and see what I get. And that's what it works out to be. Okay, what about this one? Which expression is equivalent to this one? What are some things I could do? Well, I could, if I wanted to, I could expand this whole thing out, right? I could distribute the 3x through and the negative a through and add up like terms, and then do the same for each one of these and see which one is the same. That's fine. I can do that. That's the math way of doing it, the algebra way. Is there a trick? We talked about some tricks yesterday. Anybody have a way we could fool the question here to get the answer? We can. Plug in a number for x and for a, right? Because if these are, whenever they're asking about equivalent, which is the same, which is equal to, they have to end up producing the same values when I plug in the same, when I plug in the same numbers for the variables, right? So if I plug in a number for x and for a, up here, let's just say x, let's let x equal 2 and let's let a equal 1 and just see what happens. So if I do that, I'm going to get, let's see, 2 times 3 is 6 minus 1 is 5 times 4 times 2 is 8 plus 7, so that's going to give me 15. So what's that equal to? 5 times 15. 75? Okay. So then I could do the same thing down here and just see which one works. Here I'm going to get 12 times 2 squared, so that's 12 times 4, 48 plus 42 minus 4 times, so that's gonna be way too big, isn't it? Right? I think, well, maybe not. So we get, do you agree that's 48, 12 times 2 squared? Plus 21 times 2 is 42, minus 4 times 1 times 2 is minus 8. So actually, no, it's not, it's pretty close, but it's not right. I'm gonna get 82. 82 is not 75 though, so that's not it. What about this one? I'm gonna get 48 plus 21 minus 4, right? 4 times 1, A is 1, times 2 minus 7 times 1 is 7. So what's that equal to? 48 plus 17 times 2, everybody agree? 21 minus 4. 17 times 2 is 34 minus 7. So that's going to be, what's that going to be? 82 minus 7, 75. Right? It worked. That's the one, isn't it? Now, what if, accidentally, say that this one, for some reason, also gave us the answer 75. There's only supposed to be one answer. What could I do?
Plug in different number.
Plug in, at least make one of those different. Maybe make the A 3 or something, right? And see how that's going to make one of, both of these are going to change, and only one of them will give me the right answer. Right? Awesome trick. Okay, moving on. So this is easy. We're just going to multiply like 2 of these together. I'll take 2 of those binomials and multiply them together and simplify, and then distribute the third one and add like terms. No big deal. You've done a lot of stuff like that. That was way back in 6.2. We did lots of that stuff. Okay, what about this? Now, don't get intimidated by the amount of reading there is to do. When you do tests like this, where there's lots of reading, typically that means that they're assuming that reading is going to make it more difficult, so the math gets easier, right? So really, it's not a bad trade-off. If you think about this, it's not hard. They're telling you there's this relationship for a biker's distance from home. Y represents distance in miles, R represents speed in miles per hour, and T represents time he's traveled in hours. So here's the equation that gives us the relationship, and all they're asking us to do is write an equation. It doesn't even say a simplified equation, for which the solution is the speed of the bike in miles per hour, where the bike's distance from home is 75 miles, so that's Y, isn't it? And it has traveled for 5 hours, so T is 5. All I got to do is plug in 75 for Y and 5 for T, and that's the answer. That's an equation whose solution, if I solve it, I'm going to solve for R, which is speed. I don't even have to solve for R. I could, but I don't have to, right? Make sense? Okay, let's look at one of these. I just picked one just so we could talk about a percentage in a problem once. So what about something like this here? This is where they're giving us a story and we've got to turn it into an equation, or in this case an inequality, right? So they're saying a clerk earns $150 per day plus a commission equal to 8% of his sales. So S represents his sales, so that's going to be our variable, right? How do we, when we're dealing with a percentage like that, if I'm saying 8% of something, let's just say I want to know what is 8% of 1,200. How would I find that? No. Times it by 0.08. You're right. I've got to turn it into a decimal, right? That's the idea. And then when I want to turn a percentage into a decimal, I've got to move the decimal 2 places to the left, right? So in this case, if I start off with 8%, then I'd have to take the decimal and go right there with it. So I'd get 0.8, right? There's my decimal. Right, 0.08. Okay? So then that means if I want to find, so 8% of 1,200 would be 0.08 times 1,200, right? Okay, so how are we going to write that part then? If the clerk is earning, each day he's earning $150 plus 8% of sales, which are S, wouldn't that just be 150 plus 0.08 times S, right? The other part of this tells me that on Monday, the clerk earns less than 210. So doesn't that mean that the total amount that he's earning is gonna be less than 210, right? So it's an inequality. That's all you're supposed to do. Sometimes they might use other language that you have to interpret. What if we had the same problem and it said something like he earns at least 210? How would I change this? Okay, but if he earns at least, now ask yourself, okay, so does that mean, could he earn 220?
Less than or
Almost. Greater than or equal to, right? Because if I say, how much money you got? Well, I've got at least 10 bucks in my pocket. That means, could you have 12?
Yeah.
Yeah. Might you have 8?
Yeah.
No,
Oh,
because you got at least 10, right? So you know you got more than 8, right? See what I'm saying? It kind of, yeah. But and so you got to be careful with it. You got to kind of think about that and ask yourself some questions and say, okay, would this number make sense, or would this number make sense, to see what kind of inequality it is, right? Okay, good. We'll skip that one. Okay, how about this guy? The school is having yearbooks made. Memories yearbooks charges $300. So this is you'll for sure get something like this, and these are easy. So this is one where they want you have to make a choice between two companies that sell yearbooks. One of them charges $300 up front, and then there's a $25 per yearbook cost, right? The other one charges $400 up front, but it only charges $15 per book. And so they want you to graph the functions that show the cost of buying N yearbooks. So the cost is going to be the Y variable, and the number of yearbooks is like the X variable, right? And so all we'd have to do is just graph these lines. Well, to graph a line, all you need are 2 points, right? So let's look at this first one here. This one charges $300 to set up, and then $25 per yearbook. So what's 1 point on that graph? 300 is the initial value, isn't it? The start value. So we'd start at 300. Okay, what's this 25? What would we call that? That's the slope, or the rate, isn't it? Right? So the slope is going to be, we're going to increase, for every yearbook, we're going to have to increase the cost by 25. Right? That makes sense? So then we need to be able to, and here's the only part of this that's at all tricky. We need to be able to find another convenient point on the graph so we can accurately connect them and get a good line, right? Well, notice that on this graph, the cost only goes up by 200s, right? And so that's going to make things a little bit tough. It'd be pretty hard for us to say I'm going to go over 1 and up 25. That's not going to be very accurate, is it? I want to go over an amount so that I'm going to have the point be at a convenient place, right? So for example, if I want to go from 200 up to 400, that'd be an increase of, or from 300 up to 400, that's an increase of 100, right? So how far would if every yearbook I'm going to go up by 25 to go up a total of 100, how many yearbooks would I have to go over 4, wouldn't I? So I would go 4 over and 100 up, and that would be my triangle, right? I'm going to go 4 and 100 to get to that point right there. That's a convenient point. It's where the graph crosses itself, right? And so I could just extend those lines and create the first line, right? Got to do the same thing for the other one. For the other one, let's see, we start at 400, but this time the slope isn't very convenient. It's 15, right? So how am I going to move over some convenient number of books that's going to make the change in Y going to be something reasonable? Like 150 might be okay, right? If I went from 400, let's see, that'd be 500, so 550 would be 3/4 of the way up. That'd be okay. Maybe better would be if I could go up 300, right? 15 would go into 300. So 300 would take me from 400 up to 700, right? So there's my 300 rise. How much would I have to run to get that, though? How many times does 15 go into 300?
75 twice, which is 10.
10 would be 150, right?
Just in 10 classic.
So we could say it this way if we want to. The slope is going to be, right now, the green slope is I'm going to rise 15 for every one I run, right? So if I want the rise to be 300, what do I have to multiply 15 by?
20.
20, so I gotta multiply 1
I
by
thought you were
20.
doing 150.
See what I'm saying? Oh yeah, we started off with that. That'd work, but this might be better. So then I could go over 20 and go up 300 to get that point right there. And then I could connect those two. And there's gonna, on SBAC, there's gonna be a tool you can use, right? You probably already saw one of those on the practice test. There's a tool you can use to connect dots,
Oh, yeah.
right? Okay? All right, here we go. So what about this one? Back on track. Here we go. So what about something like this? This goes all the way back to probably pre-algebra. How did you solve equations, or algebra 1 at the very least? How did you solve equations like this where they were set in fraction or ratio form? What'd you always do?
Cross.
You cross multiply. There you go, right? So if we cross multiply, whoops. If we cross multiply, one cross product is going to give us x times 5 is 5x. The other one's going to give us 1 times x plus 2. So I end up with 5x equals x plus 2. Subtract x from each side. What do I do now? Divide by 4. And I get x equals 2/4 or 1/2, right? No big deal, okay? No big deal. What about this? So this is one where the people that wrote the test think this is a really hard problem. This is designed to really, be a tough one. But we've done this stuff. What do you do when you're solving a radical equation like this? Square both sides to undo the radical, right? You isolate the radical, and then you take both sides to the power that you need to, right, to get rid of the radical. So in this case, we're going to square both sides. What's that going to give us on the left side? Okay, no, it's not. It's giving us, now here's the thing I want to make sure you remember.
P times P plus 2 times P plus 2.
P plus 2 times P plus 2. Here's the thing, one of the most common mistakes people make in an algebra class. Okay, I'm going to wait till I get everybody with me here. Okay. Is they want to distribute the exponent when you're adding stuff, but you can't do that, right? You can for multiplication. This is different. If I have something like 2p squared, well, because the 2 and the p are factors, they're being multiplied, then I can distribute it. I would get 2 squared, which is 4, times p squared. It's easier to deal with when it's a product than it is when it's a sum. When it's a sum, I can't do that, because when I'm squaring something, think what that means. I'm multiplying the whole thing by itself, right? So this is equal to p plus 2 times p plus 2, right? So I've got a couple options then. I could just expand that out, manually. I could just distribute the p and distribute the 2 and add like terms, which works. Or hopefully you remember, I think Tyler reminded us about this yesterday. What is our expansion pattern, our product pattern for a plus b squared?
A squared plus 2ab plus b squared.
Good, okay. So then that's going to give us on the left side, if I expand that out, instead of a I have p, instead of b I have 2. So I'm going to get p squared plus 2 times p times 2 is 4p, plus 2 squared is 4, right? And on the other side, if I square a square root, thank you. If I square a square root, why don't you pass that back? I just undo the radical, right? So those go away, and I just get 3p plus 4. Okay, this is a good place for us to stop and think about this for a second, though. We did a ton of these things in Module 3, solving quadratic equations. So how do we solve a quadratic equation like this? What do we have to do first before we even start trying to get busy?
Get it equal to 0.
Got to set it equal to 0. I got to push everything over to the side where a is going to be positive, where the number of p squared is going to be positive. So we'll move everything over to the left. So if I subtract 3p from both sides, how many p's am I going to have left on the... 1, right? 4p minus 3p. And then if I subtract 4 from both sides, those just go away, right? So there's my quadratic equation. Now that's an easy one. It's a little bit different looking than the ones we usually do, but we've done some like this before. It's easy, right? We don't have to think about magic numbers or anything. We're able to just do what we always try to do, which is factor out a greatest common factor. What's the biggest thing that I could undistribute? What's it gonna be? Well, I can't take a p squared, but I can take a p, right? I could divide each of those terms by p. So I can undistribute a p, and then what's left? Well, if I divide each one of those by p, we'll see what's left over. What's p squared divided by p? P. That makes sense, because if I distribute, p times p is p squared, right? P over p is equal to 1. Once again, it makes sense. P times 1 gives me p. Okay, and so then what are my solutions? What's the value of p that makes that factor 0? 0. If I set that one equal to 0, I just get p equals 0. How about that one? Negative 1. Okay, so are those the answers?
Yes.
Maybe. What do I have to do? Gotta check them, because I squared both sides. They could be false solutions, right? So I gotta go put them back into the original equation up here and see if they work. Well, if I plug in 0, what do I get? 0 plus 2, so I'm gonna get rid of, I guess let me get rid of all this stuff. So if I plug in 0, I'm just gonna get 2 equals the square root of 4. Is that true? 2 equals the square root of 4?
Yes.
Yeah. So that one checks out. 0 works, right? How about 1 or negative 1? Negative 1 plus 2 is negative 1. 3 times negative 1 is negative 3 plus 4 is 1. What's the square root of 1? 1. So I get, oh, hang on a second. That one, oh, yeah, it does work, because I get 1 on that side, not negative 1. Negative 1 plus 2 is 1, right?
Yeah.
So 1 equals 1. Check. It works too. Okay? Did they both have to work? No. Maybe one of them works next time. Maybe none of them work next time. Right? But you got to check each time when you square both sides. Okay? Of an equation. All right. What about this? Okay, so this time there's a lot of questions like this too, where they want you to, they're gonna give you 3 different equations, and in each case you're supposed to decide how many zeros are there, how many real solutions, right? So on this one, I would just cross multiply and solve for x. And if I do that, I'm gonna get, it turns out I'm gonna get exactly 1 answer for x, so I get 1 solution, right? Here's one like we just did. If I square both sides of this and solve for x, and I check the solutions, this is one where they're both gonna work. So it turns out I got 2 real. Now it might change for you, right? But if we were to do that process, we'd get 2. Here's the one I want you to tell me about. What about this guy? How do you know, without even doing anything, that that's got no real solutions? What do you think? Because, well, what would have to be true? If I isolate the radical, if I subtract 7 from both sides, look what I get. What's significant about that? It's negative, yeah. Can the output of a square root be negative? Not for a real number, right? The smallest I could get is the square root of 0, which is 0. But after that, every square root's going to give me back some positive number, isn't it? Right? So we know right away that that can't work. There's going to be no real solutions. Now, if I did solve it, if I squared both sides and solved it and plugged it back in, it wouldn't work. The solution wouldn't make the original equation true, so we'd know that it was a false solution. But we don't even have to do that, right? We can just look at this and see that it can't work. Okay? All right. We can skip that. Okay, what about this? Solve the given equation for m. What's that mean? If they give us some equation that involves 2 variables and they say solve it for one of them, what's that really telling us to do?
Isolate that
isolate the variable, yeah. So solve really means isolate, right? It's gotta get it by itself. So what are the steps we'd go through to get m by itself there? And all we'd have to do, if you can't remember the order, remember that bottom-up order of operations is isolate or solve, right? So what would we have to do first?
Multiply by 5.
Okay, I have to multiply by 5 to get rid of the 5 on the bottom, then what? Divide by 2 to get rid of all that stuff, right? Now I could do that in one step because I could think of 2/5 as being a fraction. I could just multiply by the reciprocal, 5/2 too, right? Either way, multiply by 5/2, and then I'm left with that. What's the last step? Square both sides, and we got it, right? Okay. Stuff like this, same kind of thing. For the given equation, find the value of c when f is 92. So what would I do? Good, I put in 92 for f. That's going to become a 92, and then what? Solve for c. Isolate c, right? And just get an answer, okay? Okay, all I'm going to do here is just simplify both sides, add like terms, and isolate x. And you've done a lot of stuff like that, no big deal. Okay, let's take a quick second on this one. What are the steps to isolate x here? We're supposed to solve for x. So I'm going to subtract 12 first, that's good. Then what? Divide by -3. But if I divide an inequality by a negative, got to flip the sign. If I multiply or divide an inequality by a negative number, I have to flip the direction of the inequality, right? Good. Okay, what about this? So now we've got a quadratic equation, but we got 3 quadratic equations in a row here I want to just take a quick look at. Just think about strategies. So it's been we did lots of this, but it's been a little while. What if we've got one like this where I've got an x squared, but there's only one x, right? How do I solve that one? Do I have to use factoring or the quadratic formula? I don't. I can make it much easier, right? What's our trick? We said whenever you can point to a single variable, you can, what? Isolate it. Yeah, I can isolate it. I don't have to factor this time. I can just get the x by itself. So what would the steps be to isolate x? Add 72, so I'd get 8x squared equals 72. Divide by 8, so I'd get x squared equals 9. Square root it. And so x would equal plus or minus the square root of 9, which is plus or minus 3, right? Okay, good. How about this one? So what do I have to do to this one before I can solve it?
Set it equal to.
I got to set it equal to 0. Good. I've got to add the 3x to the other side. So I'd get x squared plus 13x plus 30 equals 0. Now, what are my options for solving this? Yeah, you could. You're right. And you would, because that's the easiest way. So we could factor it. What else could we do if we wanted to? Quadratic formula. You got to know the quadratic formula, right? Got to know that. I'll put a link on the SBAC Prep to the quadratic formula song if you want to listen to that a few times to really remember it. Caitlin, I know, probably does. She loves that song. Right? Oh, you do? Okay. So if I factor this, what are the magic numbers going to be? Justin, what are the magic numbers going to be?
These are almonds are going to be the numbers.
Are they?
10 and 3.
Okay, so we get x plus 10 and x plus 3. So what are my solutions going to be?
-10 and -3.
Right?
And then
Okay. Good? Okay, what about this one? Last quadratic. So what about this guy? So we could try to find magic numbers, but are there numbers that multiply to positive 15 and add 6? No dice. Not going to work. So what do we have to do then? Quadratic formula. Okay. So it's in standard form. What's A? What's B? What's C? Okay, so then we'll just apply the quadratic formula. So x equals -b plus or minus square root b squared minus 4AC. What's 4 times 1 times positive 15?
4 times 50.
4 times
Wait.
positive.
Yeah, what is that?
45. 75.
60, there you go. Divided by 2 times 1 is 2, right? So all we've got to do then with the quadratic formula is just simplify that. So we can, first thing let's split it into separate fractions. So we get negative 6 over 2 plus or minus the square root of negative 24 over 2. So 6 over 2, negative 6 over 2 becomes negative 3. And then you get plus or minus. Yeah, what's that going to become? So the negative is going to become an I, isn't it? Right? What about the 24? Is there a perfect square factor of 24? 4. Good. I could break that up into plus or minus the square root of 4 times the square root of 6 over 2, and then the negative becomes an I, right? Okay, last couple steps here. So then we get negative 3 plus or minus, what's the square root of 4? Divided by 2, cancels, right? So there's my answers, right? Both of them. Okay? Make sense? All right. Okay. Okay, last couple. Here we go. Let's see if we can get through these. Quick, quick, quick. Everybody focus. Then this is a good place to stop. Okay, everybody up here, please. Okay. So how about this first one? First one here, we've got, consider the equation x plus 5. Okay, I'm hearing some talking. Stop talking. Plus k equals 0. So we want to find a value of k so that it has no real solutions, right? Just think about this. If this is a quantity that's being squared, I'm going to have to square root both sides to solve for x, aren't I? So what if I were going to solve for x? I'd subtract the k to the other side. And that's going to give me negative k. How am I going to get i's instead of real solutions? What if I square root both sides? Right, so that does. Give me an example. All it wants you is to pick one value of k that's going to make this thing have i's. It's going to make it non-real solutions. Well, but plug in a value for k that's going to make us have an I. So, well, k would be like 10, right? Because I've got a negative in front of it. Would you agree that if I substituted any positive number for k, that's going to give me something like the square root of negative, what if I put in a 10? I'd get the square root of negative 10, which is going to give me I, right? So any positive number would work. All right, last one. What about one like this? This is a little bit different, right? But it's just as easy. Okay, consider this equation. X squared plus bx plus 4 equals 0, where b is some real number. Find a value of b so that we have no real solutions. Okay, here's how you do this. Remember the discriminant we talked about. The discriminant is the part of the quadratic formula that sits under the radical, right? So isn't this the part that's going to cause an I to happen? Is the part, the number inside the square root? So whenever that part that's inside the radical, the b squared minus 4ac that we call the discriminant, if that's negative, I'm getting an I. I'm not getting real solutions. So let's see what that is. B squared minus 4ac is equal to b squared minus 4 times 1 times 4, b squared minus 16. So I just need to pick some value of b that's going to make that negative. So what's an example of one that would work? Pick a number that's going to make that negative.
Positive 16.
Say it.
Wait, just kidding. Not listen to what I said.
Okay, what's one that would work?
4, 2.
Now 2 would work, because I'd get 4 minus 16 is negative, right? See what I'm saying? Or 1 would work, or 0 or something, right? All right, good job.